This is part 2 of chapter 2 lecture, and in this lecture we're going to cover molecules, compounds, and bonds. So this is an image showing you what an individual atom is. We've already covered that in the first part 1, and then we're going to talk a little bit about the molecules, and in particular how those molecules form some of the bonds. So I'll give you a few definitions to start off with. A bond is just the process of 2 or more atoms coming together. So the same way you might have a bond with a friend in which y'all are very close, a bond is what happens when 2 atoms get very close or come together. A molecule is what we call 2 or more atoms that are actually bonded together. So if our bond is the space between the atoms, then the molecule is what happens when we have those 2 atoms that are bound together. So it's atom 1, atom 2, atom 1, atom 2. That entire structure is a molecule. A compound is any molecule comprised of 2 or more different elements. So you see here in this picture we have 1 and 2. This is going to be an example of a compound because they're both different. Something that is the same atom twice, so something like N2 or O2, this is an example of a molecule because it still shows 2 atoms that are bonded together, but it is not a compound because remember, a compound has to be different elements. I don't know if you've heard of the word compound, but a compound is usually made up of different little structures together that form that compound, so that's another way to think of it. And then finally, introducing this concept of a molecular formula. So molecular formula is going to be the chemical symbols along with any types of numbers. So, and you see here this molecule C6H12O6, you're going to have a chemical symbol like the C, the H, and the O. And then you also have a subscript. So a subscript is going to be a number that's below the normal line. That subscript is going to tell us how many of each of those atoms are present. So molecular formula will consist of letters and numbers. That's something to keep in mind. Molecular formula is letters and numbers. So again, we just talked about a molecular formula, which is letters and numbers, while a structural formula shows how atoms are bound together. That's actually going to be a combination of letters and lines. So if you see anything with a line in it, right, something like H2O, you have a line showing that those 2 H's are bound to the oxygen in that way. That's going to be a structural formula because you have the letters and the lines, as compared to a molecular formula, which is the letters and the numbers. Letters and numbers. So a chemical bond is going to be how our molecules are held together, and they're going to be held together by either a hydrogen bond, a covalent bond, or an ionic bond. So again, you have to ask yourself, what part of the atom interacts with other parts of atoms? So what part of the atom is going to interact with the other parts of atoms? It's going to be the electrons on the outside. That's the valence electron. So let's get back to those electrons. We haven't talked about them so far in this video. So this brings up the octet rule. Anybody knows octet is going to typically represent something that is the letter 8. So if an atom has 2 or more shells, which most atoms do, the valence shell is stable when there are 8 electrons present. I'm going to explain why that number is 8, but when we have 8 electron presence, the valence shell is stable. If an atom only has 1 shell, is stable after it has only 2 electrons, and that's because remember on that very first shell, so that's my little nucleus, the dot, that first shell has 1 orbital, and every orbital can hold a maximum of, guess how many? 2. So if it only has 1 shell, it is stable at 2. The reason our atoms are stable at 8 if they have more than 1 shell is if we're looking on the outside shell, remember we have 4 orbitals. Each orbital will hold up to 2 electrons. So if we were to fill up each of these orbitals with the 2 electrons that they hold, then it will be stable or it will be full at 8. Because of this, an atom will do anything to gain, lose, or share an electron to have 8. Okay, so 8 is the magic number. That is the number we're striving for, and an atom will do just about anything to be able to fill up these orbitals so that it has a full outer shell. So the first type of bond that we will cover, and it's probably one of the more challenging bonds, is a covalent bond. So this is a bond where the electrons are shared. Anybody has shared something, we'll talk about the good things and bad things about sharing. Sharing is good because it makes the bond strong. So covalent bonds are the strongest. That's because if you're sharing an electron, both of them have control over that atom. Think about individuals that have conjoined body parts. So if you and your Siamese twin share a leg, then it's going to be very hard to separate that leg. It's not your leg, it's not my leg, it's our leg, right? That's because it is shared. So the same way that is a very, very strong bond for a body part, it's going to be the same thing for these covalent bonds. However, if you've ever shared anything with anybody, you know sometimes people share things unfairly or unevenly, and sometimes you share things evenly. We're going to get back to that idea, okay? A covalent bond is going to represent a pair of electrons. So if we ever say there is a covalent bond, we're talking about a pair. Remember, a pair of anything always represents 2. So one pair of electrons is going to be a single bond, like HF, and that's going to represent 2 electrons. 2 pairs of electrons is a double bond. That's going to represent 4 electrons because it's 2 pairs, right? It's this pair and it's this pair. That's how we end up at 4. And then, of course, triple will represent 6 electrons. The octet rule will help us to determine the number of bonds an atom has. So example is oxygen. So oxygen is an atomic number of 8. And if we're looking at the octet rule, we have space here and we have space here. So we can put an extra electron there, an extra electron there. That means oxygen has the ability to form 2 bonds. Our magic number is 8. We already have 6 if you were to count the electrons oxygen has. So you have the ability to form 2 bonds. Nitrogen, we have the ability to form 3 bonds. Carbon is very special because my picture's a little bit cut out, but carbon has 4 electrons on the outer shell, which means it has 4 spaces for bonds. So the 8 minus 4 that are already there will allow us to have 4 bonds possible. Again, this is just another image showing some of the different types of bonding we have. So polar covalent bonds, I'm going to give you a hint. If you have a polar covalent bond, that means you have uneven sharing. So anytime you see covalent, that means you know there's going to be some electrons that are shared between the 2 atoms. But polar means there's going to be an uneven sharing between those 2 atoms. So there are reasons as to why those electrons are not shared equally, and let's look at them. The major reason is because the atoms differ in their electronegativity. They differ in their electronegativity. What is electronegativity? Electronegativity is the affinity. Affinity is like attraction. So another word for affinity might be attraction. It's the affinity for electrons in a covalent bond related to the size of an atom. So does the atom A have a higher attraction or pull of electrons, or does atom B have a higher pull or affinity for electrons. That's why we have this picture of the tug of war, right? Imagine this is atom A, this is atom B. Which one is going to pull electrons to its side? Which one is going to unfairly hog or take electrons? So again, electronegativity is the affinity an atom has for electrons. How much is it trying to say, instead of us sharing this equally, come over to this side? Instead of us sharing this equally, come over to this side. Larger atoms have a higher affinity and higher electronegativity. The reason why larger atoms have a higher affinity and electronegativity is you have to think about some basic principles. If an atom is larger, that means it has a higher atomic mass. Its atomic mass is composed of its nucleus, which is composed of positive protons. A smaller atom, I'll just draw it over here, is going to have a smaller nucleus, meaning it has less protons. Remember, an electron is what charge? Electron is negative. So negative things are drawn to positive things, correct? So would you assume that this negative electron goes towards all of these positive protons, or would it go towards these few positive protons? It's going to go towards the most positive protons it can have. So larger atoms have a higher affinity and higher electronegativity because the reason it's larger is inside of its nucleus it has more positive protons, and the positive protons are going to be attracted to the negative electron. So that electron is going to start to slowly go this way. So instead of staying right in the middle where it's supposed to, it's going to start leaning a little bit towards that left. What this is going to do is it's going to create a polarity or a difference in charges in this molecule. So let's say we're talking about this same structure. Assume I put 10, well, how many pluses did I put here? 1, 2, 3. I put 8 pluses in this atom, because remember, if it's 8 positive, it's naturally 8 negative. This one is 2 positive, 2 negative. If I start taking up more electrons, I'm going to take this 8 number and I'm going to add an additional electron. I am hogging this electron. So now instead of having 8 electrons, I really have 9 electrons. Because this electron in the middle is going towards the left, this atom to the right will start to look more like -1 instead of -2. So this atom on the right is going to be a little bit positive, and this atom on the left is going to be a little bit negative. Because if I have 8 positive and 9 negative, that means I'm a little negative. And if I have 2 positive and only 1 negative, that means I'm a little positive. Okay? So again, to reinforce the idea, electronegativity is when an atom can pull or try to attract electrons. This electronegativity is related to its size, where larger atoms have a higher pull because they have more protons. They are going to naturally pull those electrons towards it. Once it pulls those electrons towards it, instead of sharing fairly, it's going to kind of get an extra electron here, and that extra electron makes it a little more negative. So this side of the molecule is a little more negative, and because the smaller molecule lost an electron, instead of having 2 electrons, it kind of has 1 electron. This is going to make this side a little more positive. This is a big concept. I completely get it. Please rewatch this if it doesn't make sense. I have another example on the next slide if you want to watch that before you decide if you need to reconsider. So again, for electronegativity, Think about you being a college student. Maybe you need money. That doesn't really mean you're a college student. I guess everybody needs money, right? You need money. This is the electron in the middle. If you're supposed to fairly stay in the middle, and you have an option to go over here where you're promised $1,000, or over here where you're promised $10, where do you think you will go? Big red flag. You're going to go this way. Right? That same exact concept is what happens with electronegativity. The larger atom is going to pull the electrons that we're supposed to be sharing. But when it does that, the larger side becomes a little bit negative, and the smaller side becomes a little bit positive. So again, if you don't understand the covalent bonds, this is where you want to rewatch the video. So another example of what's happening here, seen with real atoms, is our bonds between H2O. So if you're looking at the individual atoms of H2O, you have a pretty large oxygen atom here in the middle, and then you have the smaller hydrogens on the side. The same thing that we talked about occurs here. So oxygen is bigger, it's more electronegative, so it's going to pull those electrons towards it, and because it pulls those electrons towards it, it's going to be a little more negative on the oxygen side and a little more positive on the hydrogen side. So H2O is an example of a polar covalent molecule in which you have uneven sharing of electrons, and the hydrogens are going to be slightly positive while the oxygen is going to be slightly negative. So we know what uneven sharing looks like. This is an example of even sharing. So nonpolar is going to be even. I like to think of nonpolar as non-fighting, right? They're not fighting over the electrons because they're sharing them evenly. This is going to occur when an atom has a similar electronegativity to each other. That means there's not going to be a stronger pull either way. So let's say you have an electron in the middle, and you have something that's 7 positive over here and 7 positive over here. It's going to be right in the middle. One side is not bigger than the other. So what occurs there is you don't have any charges in that molecule. You're going to have a nice, even, non-charged molecule. So that's going to happen with non-polar covalent bonds. This is the easy one. A lot of times you see non-polar covalent bonds with molecules that are the same. So if you see something like O2, N2, it's going to be 2 nitrogens, 2 oxygens, and of course it's the same atom, so there's not going to be a difference either way. So that's covalent bonds when we share electrons. Now let's talk about the type of bonds you have when we're referring to a charge. So an ion is going to be an atom or a molecule that has either gained or lost one of its electrons. So remember, let's start off with our normal element. You have, let's say, 10 protons and 10 electrons. So we basically have 2 options that can happen. You can either gain an electron or lose an electron. So let's look at what happens either way. So let's say we're going to lose an electron. If we lose an electron, our protons stay the same, because we're not talking about them. We're losing an electron. So if we have 10, we lost one. Now it's going to be 9 electrons. That's going to lead to this atom having a positive charge, because now you have one more positive subatomic particle as compared to your negative subatomic particle. So this is going to be an example of a cation. And I like this word because there's a T there, and that T should help you remember positive. So cations have a net positive charge, and this is what happens when you lose an electron. Very important that you understand the relationship between losing an electron causes you to have a positive charge. So if you lost something negative, you're going to have more positive subatomic particles there. Let's look on the flip side. If you were to gain an electron, we still have 10p, but now we have 11e. So this is going to lead to an overall negative charge. That's an anion. And anions have net negative charges, and this is what happens where you gain an electron. If you're not a fan of onions, you think they leave a negative taste in your mouth, then maybe anion kind of is related to onion. I don't know. So an ionic bond occurs when a cation, something that's a little positive, interacts with something that is negative, an anion, and it's just a electrostatic attraction. A great example of this is salt. So we tend to call our ionic compounds salts. And examples are, of course, sodium chloride, which is typical table salt that you put on your food. And then, of course, things like potassium chloride or calcium chloride. Those are other examples of salts. Our final type of bond is a hydrogen bond. And a hydrogen bond kind of brings in the principles of ionic bonds, which are the natural positive and negative attractions, and also talks about the covalent bonds in which one of the molecule kind of takes too many electrons and it leaves a partial positive, partial negative charge. So what happens in a hydrogen bond is the hydrogen atom of one polar molecule, that's our covalent polar molecule, is attracted to the electronegative atom of another polar molecule. Let me explain. So let's say we have H2O. We're going to use that example. We have an oxygen. We have two hydrogens. We already talked about how oxygen is bigger, so it's naturally going to kind of pull those electrons to make it a little negative, and the hydrogens lost an electron, making them a little positive. That's what we learned for covalent bonds. Let's say this oxygen is in, or this H2O is in the presence of another molecule of H2O. Right? What happens here? We're going to see that oxygen again is still negative, and those hydrogens are still positive because it's a polar covalent molecule. But what is new is you're going to start to see this little bit of an attraction between the hydrogen molecules. Okay? Let's say I were to do this down here. I'm going to draw another little picture of a water molecule. Same concept. You're going to start to see some of the attraction between the hydrogen molecules and the electrostatic or the electronegative molecules. So here. We tend to draw hydrogen bonds by showing dotted lines. So anytime we show a little dotted line, that means there is a slight attraction. I like to think of this as like a crush, right? It's not very strong. It's not a bond, but it's, it's kind of there, right? So again, positive hydrogen interacts with the electronegative or the negative atom of a polar covalent bond. So hydrogen bonds, you have polar covalent molecules. They naturally will have slight charges, and from those slight charges, the hydrogens are going to start to interact with the negative electronegative atom. Individually, these bonds can be pretty weak, but what happens is if we have a lot of them at one time, it can form a strong bond. So an example is sometimes you may have seen these little like gnats or kind of insects that look like they can walk on water. That's because there's hydrogen bonds in the water molecule. So the weight of the insect is light enough so that it doesn't break those hydrogen bonds. That's why it kind of is able to walk on water, for lack of better words. And again, like I said, these bonds can be pretty strong. So this is another image showing the hydrogen bonds. Again, I wanted to reinforce you have polar covalent molecules. Out of these polar covalent molecules, the hydrogens, which are a little positive, they're going to start to interact with the oxygens, which are a little negative. So again, hydrogens, a little positive, interact with oxygens, a little negative. We show that by the dotted lines. Okay, so this is wrapping up the section talking about the different bonds we have, ionic, covalent, and hydrogen. If this makes sense to you, then you can move forward. If you are a little stuck, then I would recommend you go back. So we're going to use that same scale between clueless, like I have no idea what you're talking about, and an expert of yes, I can explain it to you in class. I want you to be somewhere around the 7 to 8 mark. I know we're going to fill in some more questions in class, but again, this is where I want you to dig deep and make sure you try to understand it. So when we get to those questions, you'll be prepared. Thank you.